Jupyter Notebook, I've imported pandas and NumPy, and then I've also done the import for matplotlib so I can do a little bit of plotting for two arrays, which is matplotlib.pyplot as PLT. And then I've also set matplotlib inline, which you may not need to do depending on what version of Jupyter you're using. Okay, we're going to go ahead and use some sales data for beer and liquor. So we'll say df is equal to pd.readcsv. And underneath the data folder, in fact, I think I'm actually located at the top level right now. So underneath data, go ahead and open up the alcohol_sales.csv file. The index column will be in all caps date. And then we'll say parse dates is true. And then after this, we'll set df index frequency is equal to capital M, capital S. And then we'll go ahead and run that. And if you check the head of the data frame, it should look something like this. So right now, because I downloaded this data directly from Fred, and in fact, you can always check out the link in the notebook. So if you click on the link in the notebook, it'll show you the actual information, what this data set looks like, and then if you want to download it yourself again, and more information about that data. But you'll notice that it always carries the kind of weird column name of the actual ID code here. So what I'm going to do is just rename this. So we'll say df.columns, and there's only one column, so we'll say df columns is equal to, and then just pass in a list of the single column name, and I'm just going to say sales. Which means now I can plot out the data frame, say fig size is equal to, and we'll say something like 12 by 8, and here we can see the actual sales cycle. So it definitely looks like there's some sort of seasonality to this, and there's also some general trend that's growing. What we're going to do now is we're going to decompose this into its separate components. So we'll say from statsmodels.tsa.seasonal, I'm going to import seasonal decompose, and then we're going to run seasonal decompose on that actual series. So we'll say on sales, and then that is my results, so to speak. And then we can always, off of results, call .plot, and we'll see the plotted out results. So I can see the true observed data, and if you're seeing double, go ahead and add a semicolon there. We can see that there's definitely some seasonality component, and then we can also see the general trend. And if you want, remember, you can always grab the separate trend components or seasonal components off of this. So you can say results.seasonal, and then just plot that out. And since this is just a series, you can also set figure sizes, like 12 by 8. Unfortunately, you can't do that with the entirety of results because it's kind of a specialized stats models object. But once you just call .seasonal, as we've talked about before, or .trend, that's just a normal Panda series that you can call .plot off of. Okay, so you can go ahead and explore those. And just in case you ever get stuck, recall that we always have the notebook here for you. So later on, the Keras code may get a little complicated, so you may want to reference that. But here you can see that we kind of plotted them out each separately to get a little better look. So we can tell that there's definitely some seasonality. So it'll be interesting to see if the recurrent neural network can actually cope with that without us telling explicitly what to look for. So let's go ahead and do a train test split. That way we can train our neural network on the training data and then forecast into the future. We can forecast as far as we want. So we'll forecast into the test data range so we can compare the results. So if I take a look at the current length of my data frame, it's just df. And let's go ahead and check out the data a little more closely. And we can see here that the date, it's monthly data. So we have a monthly start frequency, which means I'm going to go ahead and forecast 1 year into the future. So about 12 points into the future, which means if I just do a little calculation here, 325 minus 12, my training data set should go all the way from the beginning to index point 313. So I'll say my training data is equal to df.iloc from the beginning all the way to point 313, and my test data will be df.iloc from 313 all the way to the end. So if I take a look at my test data, it's now those last 12 points. And I can confirm that simply by checking the length. So now my test data is the last year. And now we're going to start getting into things that are specific to Keras. And typically, when you're running a neural network, what you're going to have to do is you're going to need to scale the data or normalize the data. There are lots of different ways that you can scale data. One really simple approach is to just divide by the maximum value. And let me show you in a kind of a simple context what that would look like. Let's imagine that I have some series of information. And in fact, I'm just going to do this as a normal NumPy array. So let's say I have the numbers 23, 56, 2, 13, and 14. You don't need to copy these exact numbers. If I wanted to normalize all this data so that the essential scale between the numbers stays the same, but the overall range happens to fall between 0 and 1, what I could do is simply calculate the maximum value of my array. So do a little search here and realize that it's 56, and then take my series and divide it by that max value. And when you see the result here, what happens is the max value ends up being limited to 1, and then everything else gets scaled, falling in between 0 and 1. So that's a really easy way and simplified way to go ahead and scale your data so that it all falls between 0 and 1. And as we know with neural networks, since we are calculating biases and weights, if we have data that's too skewed off, maybe your smallest point is kind of way lower than your highest point. So for instance, our time series, our lowest point is in the 4000s, and our highest point is almost like in the 15,000s. That could be enough where neurons start getting confused as far as what values of weights and biases to use, since there is such a difference in scale there between your minimum value and your max value. So what's nice about this is if you divide everything by the max value, you now have all numbers falling between 0 and 1, which is a much smaller scale and overall usually leads to better results in your training. So what we can do is we can automatically scale our data using a scikit-learn. So we'll say from sklearn.preprocessing import min-max scaler. So this is kind of an automated version of what we just did here. And this first part of finding the max is essentially the fit. And then this part of actually dividing by the max is the transform. So what we're going to do here is we create a scalar object. So we say min-max scalar. So there's an instance of the scalar object. And then the scalar object essentially has two main things it can do. It can either fit or transform. And it actually does have the functionality to do both at the same time, fit, transform. But we're going to see in a little bit why we're just going to say fit and transform instead of fit, transform. So what I'm going to do is take my scalar and fit it just to the training data. So we only fit to the training data for this particular scaling process. Otherwise, if we were to fit to the entire data set, we're cheating a little bit by assuming future knowledge about the test set. So typically what we're going to do is when we're evaluating our models and we're scaling our data for a neural network, we only fit this scaling procedure to the training data. Because in real life, you're only going to be able to scale to your current known data. And then forecasting into the future, you're not actually going to know the scale of that data. So that's why we have this scalar only being fit on the training data. So what does this fit process actually do? Well, it actually just finds the max value in the training data set, or whatever we happen to pass in here. But since we're passing in training data, the fitting procedure just finds that max value in the training data. Okay, now keep in mind, you may get a warning here, and the warning is actually just a little data conversion warning that in order to do some operations internally, if it has integers, it's going to convert them all to floating point numbers, which makes sense because if everything's falling between 0 and 1, you want to make sure that you're able to allow decimals. Otherwise, everything would have to be either 0 or 1. And you can see the same thing happened here. We had integers here, but when we divide by max using NumPy, everything turns into floats, which again makes sense because the values are going to be in between 0 and 1, so you need floating point values. So don't worry about this data conversion warning. It's totally safe. Okay, so now we have this min-max scalar object, and then what we're going to do now is we're actually going to transform the training data and the testing data. So we're going to say scaled version of my training data is equal to the scalar dot transform, and then I'm going to transform the training data. So what does the transform procedure actually do? It simply just divides by the max value essentially. So if you take a look at min-max scalar, it will actually tell you what it does in details here. So I mentioned that the kind of simplified version of thinking about this is dividing by the max value. It's not exactly what the min-max actually does. In fact, you can see that it's actually going to use a bit of the standard deviation. So it's going to use both the minimum value and the max value, and you can see the full equation here. So technically, min-max scalar is not doing something as simple as just dividing by the max value. Dividing by the max value is just a way I like to show students, that way they kind of get an idea of what's going on behind the scenes. If you wanted the full equation that min-max scalar is doing, simply call the docstring on min-max scalar, and it will show you how it's actually calculating this. So it's slightly more complex than just dividing by the max value, but the idea is the same. It's going to basically fit everything to fit between the feature range 0 and 1. Now, you can also scale to different feature ranges, which is why when you use this more complex formula of the standard deviation, you can actually shift everything to be between 0 and 10, for instance. So that's why the min-max scalar, the true formula, is a little more complicated than just dividing by the max, but it's still kind of useful as a thought experiment to think about what's happening here. We essentially fit by finding the max and transform by dividing by the max. In this case, for min-max scalar, when you're calling .fit, all it's doing here is it's calculating the standard deviation, the minimum value, and the max value. That's the transformation. That's the fitting part, excuse me. The transformation part is actually kind of running this equation. Okay, so again, not too complicated here. Essentially, take the standard deviation and multiply it by the max minus the min value plus that minimum value again. And this formula then expands to being able to fit for any desired feature range. So we have the min-max scalar. Now it's time to transform our scale data. So we'll say scalar, transform on the test set. So now we have scaled train and scaled test data. And now it's time to actually use these with our time series generator object. So what we're going to do in the very next lecture, we're going to continue with part 2 and learn about the time series generator object, which is a very convenient tool that Keras provides us that takes in sequence of data points gathered at equal intervals, and then it will kind of return batches of them for us. So we'll go ahead and see that in the very next lecture.